Hey everybody, welcome back to Adventures in Machine Learning. I'm one of your two co-hosts, Ben Wilson.
And Michael Burke. Hi, everyone.
Before we pressed record on this episode, we were talking through what are we going to talk about today? And we said last time that we were going to talk about how to tune, and something that there's not a lot of, when you look through a framework API doc and you're seeing, okay, how do I use sklearn random forest? There's going to be an example in there, and you're going to see some intentionally simple code that's meant to show off just the functionality, like the core functionality of that model. Like, hey, here's my training data, here's my features, and then here's my target variable, and that's in my fit or my train. There's not a whole lot else that is in those examples because it would be very confusing from the development team to have to write all that and sort of take away the signature of that particular API call from an end user. They'll be looking at just a wall of text of stuff that they're not interested in right now. But when you look at all of those examples that are throughout the documentation, you never really see everything put together and like, hey, how do I do tuning properly? And before we get into the implementations and stuff like that, we wanted to start off talking about why we tune and what is it for? Doesn't the model do that by itself? And what are all these parameters that are associated with the model?
Hey folks, this is Charles Max Wood from Top End Devs, and lately I've been working on actually building out Top End Devs. If you're interested, you can go to topenddevs.com/podcast, and you can actually hear a little bit more about my story about why I'm doing what I'm doing with Top End Devs, why I changed it from devchat.tv to Top End Devs. But what I really want to get into is that I have decided that I'm going to build the platform that I always wished I had with devchat.tv, and I renamed it to Top End Devs because I want to give you the resources that are going to help you to build the career that you want, right? So whether you want to be an influencer in tech, whether you want to go and just max out your salary and then go live a lifestyle with your family, your friends, or just traveling the world or whatever, I want to give you the resources that are going to help you do that. We're going to have career and leadership resources in there, and we're going to be giving you content on a regular basis to help you level up and max out your career. So go check it out at topenddevs.com. If you sign up before my birthday, that's December 14th. If you sign up before my birthday, you can get 50% off the lifetime of your subscription. Once again, that's topenddevs.com.
Exactly. So when you're building a model, often the first step is to do EDA. That's debatable in a production environment. You might want to build the pipeline first, but when you're just doing simple modeling, just let's say for an insight for your organization, the first thing you usually do is explore the data. The second is you might fit some basic models. And then in the later stages, you try to optimize those models that you've started with. And when you're optimizing, often that can involve feature engineering, but it also, a big part of that is hyperparameter tuning. And so taking a step back, the whole purpose of hyperparameter tuning isn't to optimize training accuracy. It's to optimize out of sample accuracy. So we want, again, models to generalize. That's the whole purpose of modeling in general. And so with that, you have a lot of power in what parameters you select to tune, what parameters you don't select to tune, and how you do that. So Ben, do you have some insights onto what are some default parameters that might not be the best for generalization?
Sure. I always default to, whenever I just talk about this stuff with people that are working on projects, I always like to default to decision trees, usually because those algorithms have the most amount of knobs associated with them. And they're the easiest to conceptualize when you're talking about, okay, if I change this parameter, what is it actually doing? Do I have to go up to a whiteboard and write the equation for this model in order to understand what the hyperparameter is doing? You don't typically have to do that when you're talking about this with decision trees or random forest or any of the associated algorithms. But the approach is the same, which is step one in any of these hyperparameters is to read the docs, which means what did you import at the top of your script or your module or at that point above your class or your functions where you're calling this particular module or this package. If you're importing sklearn and you're not pinning a version of what you're importing in like your setup.py or in your environment file, conda environment, whatever, look for the latest. If you're not pinning, if you are pinning, then look for that specific version. Go to the internet and search for that particular package's homepage and then go to the docs and find that exact version. If you're pinning, don't look at the docs for the latest version. There's a high probability that the docs are going to be outdated compared to what you're actually using. They're just going to be reflective of whatever the most recently released public version is. Then go to that particular module that you're importing. If we're talking about decision trees, we're going to be looking in classification and look for the decision tree classifier. If you're talking about regression, go to the regression, decision tree regression. And then don't look at the README style documentation. There's no guarantee that that's going to be completely up to date with the API docs. It should be. sklearn, it definitely will be, but not all packages that you're looking at are going to be like that. But nothing is guaranteed to be as correct as what's in the code. So there's always going to be a link. It's usually color-coded if you're looking on readthedocs.io, when you click on that name of that class, it'll take you to like the Python docs. And there's a particular formatting that will be generated from most of the stuff that's on readthedocs.io is Sphinx docs. So it's a package that automatically generates HTML from your code doc strings. So click on that, and then you're going to see the name of the class, and you're going to see its initialization parameters. Below that, you should see a wall of text that's going to explain what each of those parameters are. Always look at that. Look at what those parameters are doing. And if you don't understand something, there's usually going to be a link on anything that's complicated in there. If not, just search the internet for that term and try to find what the heck this thing is. Most of it for decision trees, it's all pretty self-explanatory if you understand how that algorithm basically works. You're like, oh, maximum tree depth. That's telling me how many splits it can do from the root, the top of, like, say, all of the data. How many slices horizontally can you move down through of conducting splits? There's going to be other stuff in there like maximum number of iterations. And that's as it's going through and it determining where to split. If it can't find good candidate splits on where to make a decision on how to split the data, it'll recurse and it'll go over itself again and use a different seed value to conduct the split. And you don't want to keep on doing that indefinitely, because that just means you couldn't converge. There wasn't a decision that could be made. So all of these algorithms, linear models do the same thing. Deep learning does the same thing as well. When it's trying to converge and optimize to an optimal solution, if it has to keep on retrying, it'll short circuit. Other things that are in there, like maximum number of leaves in the tree, which is the terminators, the last point of the tree split, number of candidates per split. So in a leaf node, in the training set, how many candidate rows were actually put into that leaf from a split? A lot of the defaults are pretty good for some of that stuff, but understand that that's a factor of a test data set or a series of test data sets when you're thinking about that. And it's also something that is intended to be tuned. If you set something like, number of elements in the leaf in any of these tree-based algorithms, if you set that lower than the default, that might be good for picking up extreme edge cases that you actually want this thing to be aware of that are extremely rare, but you want it to be somewhat accurate every time it sees that. That could be useful for your data set. But if you have a lot of these outlier events that you don't want to catch in some specific way and you want it to be more generalized, then that number should go up. You might say, hey, I want no less than 25 in order to consider a split to be valid. And that'll force on that split saying, hey, I need at least 25 things that explain this reduction in variance in order to say that the split is a proper candidate. So very important to analyze your data, just as you said, as part of that EDA layer of working on something. You should have some understanding after doing EDA, like what does that feature look like? And if you're doing pairwise comparisons of features with one another, you can start getting a feel of what those interactions might be when you start plotting them. Feature one plotted against feature two. If you see this extreme hotspot, it's not apparent. If you look at feature one in isolation, you're like, oh, that kind of looks like it's uniformly distributed. It just looks like this big shotgun blast when I plot it against the target. But when it's plotted against feature number two, you now have this bimodal distribution. You're like, wait a minute, when feature two is low and feature one is high, I have this cluster of data points at the extreme, location within this graph, and then everything else is isolated. There's this big void region in this graph. that's going to tell you that when splits are being considered, that's probably something that the model is going to learn. I mean, that's what it's designed to learn, is that isolation. You just reduced variance in your model by splitting at that condition. And other models like SVM, for instance, that's entirely what it's designed to do, is to create planar separations among data so that you can, sort of segregate those predictions. And then there's other things that, like stuff like your learning rate and sort of the underlying variance calculation modifications to some of the factors that go into that equation. If you start tuning those in one way or another, or just leave them default, you could be hampering its ability to optimize quickly, or you could be hampering its ability to generalize. You could get it to optimize really fast, but it's going to just be really good at predicting exactly what the training data is.
So yeah, if let's take random forest as an example. I quickly looked up the sklearn docs. We got n estimators, criterion, max depth, min samples split, min samples leaf, min weight fraction leaf, and there are like 10 to 15 more. So you play with all those. But Ben, if there was one hyperparameter that you would mess around with in a tree-based model, and let's specifically say random forests, what would be your first instinct to explore?
I wouldn't do two. Whenever I'm doing generalizable estimation of tuning for tree-based, I always do, for random forest at least, number of trees, and I always do max depth. So those two combined with one another is going to more dramatically influence the estimation that you're going to have of the stability of this model as a solution to your problem, or a tool to use to build that solution. And the reason I say that is if you have the number of trees in your random forest and all of a sudden the model completely falls apart, it no longer generalizes, it overfits like crazy, or worse, it just underfits, and you're working on a binary classifier and all of a sudden it's a coin flip probability when you drop the number of trees by half, that means there's something wrong with your features. Generally, that leads me to think I have too many features or too many irrelevant features. And the only time I'm getting a good signal is by bumping up the number of trees. Usually when you go up in tree count, it's the law of diminishing returns. You're going to get to some optimal accuracy point, and anything above that is irrelevant. You're not really going to move the needle. At least you're not going to move the needle in the way that you want based on the amount of money you're giving somebody to run that. And then the depth is probably biggest knob that you have for that bias variance trade-off with respect to over or underfitting or being pretty well generalized. And the depth becomes a problem when you're just splitting too much. So the deeper that tree is allowed to go, and there's a fun thing that you can try with this actually. If you take an open source data set and go into the configuration for any tree-based model, set the max depth to your row count, see what happens. Provided that data set is relatively well distributed amongst all of its features and it's not something that's incredibly obvious to converge on, you run and also you'd have to set min samples per leaf to 1. If you do something like that and force it to not generalize, force it to overfit on train, and then you visualize that tree, you'll just see this massive tree that's been created that might have just 1 or 2 or 3 elements per each leaf node, per those conditional statements. Like, hey, if you follow the logic down from the top of the tree, from the trunk, so to speak, down all of these branches, you'll start seeing that to get to a final split condition, you had to touch basically every feature. Sometimes many times you touch each feature. Like, hey, if it's less than 117 and feature 2 is greater than 83 and feature 1 is greater than 117.1 and feature 2, you start looking at that conditional statement where it's rapidly bucketing that conditional of all of those combinations of the features in such a way that the probability that something in holdout or in the real world is going to actually follow that decision path is extremely minimal. And that's overfitting. It's basically saying, hey, I've tried to exhaustively explore every possibility that exists within this data set, and I got it covered. And your model's massive. And when you run it against holdout or against real world data, it's going to perform very poorly. It'll be really accurate on stuff that it's seen before, like really accurate. But on stuff that it hasn't seen before and can't match those conditionals, it's going to be somewhat problematic.
Yeah, exactly. Max depth is a really powerful tool and powerful parameter that allows you to essentially determine how much you over or under fit and therefore how much you generalize. That's also my default. Then for the number of trees, it's like sometimes number of estimators on the package, or there's different names for it. You often see an exponential decay in the returns on that parameter. So the difference between, let's say, 10,000 and 100,000 trees might be negligible for your set, but often there you can sort of see an elbow in the number of trees relative to your accuracy. And as you increase the number of trees, you often increase overfitting. And so it's important to look for that elbow. And there's actually packages that plot that elbow and give you a really nice visualization of what's going on for that optimal value. So I completely agree. But Ben, I was wondering if you ever changed the splitting criteria, because there's all sorts of splitting criteria like Gini, variance reduction, etc. Do you ever play with that, or do you just use defaults?
So for something like decision tree classifier, you got 2 in sklearn, which is the best or random, and best would use one of those solvers based on the criterion. So Gini, entropy, log loss, depending on how you want it to figure out where to make that split as a potential candidate. It's never something that, like if I'm doing a problem where I understand that I have a particular style of data, some sort of distribution, and I have an edge case scenario where I have like huge class imbalance, or there's something about the distribution of either each feature on its own or interactions between features where I see, oh, there's a logarithmic relationship between these, or I have this multimodal signal that's present within a continuous feature that I might not have the data that explains that latent effect. I would definitely test those things out, but I test stuff like that usually rapidly at first. So I might do a quick run where I'm not going through exhaustive hyperparameter searching. I leave everything as maybe defaults, or I'll go through and with the default left for sklearn, that's Gini as its optimizer or split criterion. And I might tune maximum depth and min leaf size for my row count effectively. There's a huge difference between doing a dummy data set of 10,000 rows in sklearn, which is what most of the open source examples are, 10,000, 20,000, 30,000 rows. Huge difference between that and 20 million rows of training data about what that number of samples in the leaf should be. So I'll scale that stuff, tune stuff manually, run a couple of experiments to see where should I kind of ballpark be at with this in order to get some somewhat better results. But I'm not going to go into full-blown hyperparameter tuning at that stage. I'll find something that's the best of a blindfolded dartboard throw, and then I'll check that criterion and I'll say, hey, am I using the right, the right criterion splitter for this particular use case? For the most part, those algorithms are like with sklearn and with Spark and a lot of the other ML libraries that are out there. The people that built it put in usually an auto function, which is usually the default. And that's their best guess estimate of a clever way of analyzing the data that comes in, doing some quick validation and saying, based on prior research and academic white papers and tests that they've done, hey, this decision that we're making is probably right for 90% of the use cases. So I usually leave that stuff alone at first. If I don't need to touch it, I'm not going to touch it.
Got it. That makes sense. Yeah, because there's a like 20 or 30 parameters. You can't go into each one. So I was curious. Another question on that before we move on to regression-based models or linear regression-based models is how important is it to know what's going on under the hood? Like if you change parameter XYZ to 5 instead of 10, then you see a better out of sample accuracy. Is that good enough?
I would argue, and this may be an unpopular opinion, that it is incredibly important for a data science practitioner you might not need to know how to prove the theorem that model was built around. You might not need to have that level of understanding. It's great if you do. And if you work for a very large company, it behooves you to have a couple of the people that can like deeply understand the mathematical proofs around these things. But if you're a practitioner trying to solve a problem using these libraries and you have no idea how this thing works, how this algorithm works, what are you going to do when it starts misbehaving? Or when you're searching in the wrong search space, or because of something in the data, every time you train it, it's now behaving differently than when you first built it 3 months ago. If you don't know how that algorithm is doing what it's doing, you don't know how to analyze your data to explain how to fix it. You don't know how to do a root cause analysis because that algorithm is now a black box. And people say that term all the time about like, oh, this model's it's a black box model. It's like, yeah, the predictions are relatively unexplainable to lay people, and a data scientist isn't going to look at predictions and be able to explain, just looking at those predictions, how that model arrived at what it was printing out. But no model is a true black box from an architecture perspective. It is a known thing. Otherwise, it never would have been developed in the first place. It's something that code is instructing this thing to behave in a certain way. And you don't need to know how to go through and do a code review on the source code. That's overkill as well. You don't need to be able to look through the implementation of sklearn.tree.randomforest and be able to write a code comment line on every single line within that entire class path. But you should be able to understand what the concepts are, what all these parameters are doing to that model, and where to go in the code and how to look through the code to be able to read it and understand what it's doing. Like, oh, that's why it's taking so long to train this time, because it's recursing over something here. There's a for loop in the code, and that's why this particular thing is taking so long. And understanding that, how to read the code and link that up to the theoretical understanding of what that algorithm is doing is going to help any practitioner out a ton.
Got it. So one more question on this. As someone who doesn't know everything, I'm sure a lot of our listeners also don't know everything. How do you know when you know enough?
Well, let me answer that in a contention way. Also, as someone who doesn't know everything, and I think the more that you learn about these topics, the more you understand you don't know. And if you walk into this profession and you're like, oh, I can make some really good models, or I was really good at this competition that solved this. I got the best score out of 500 people that tried this example. I must know a lot about ML. Any serious practitioner that's been doing this for a while, they may be able to get a great score on something like that. They may be able to beat everybody else, or they might not even place in the top 50. Who knows? But most of those people don't care. They're too busy solving real world problems and applying the knowledge, but also applying the knowledge of where to go to look to learn more for the things that are important for what they're trying to solve. So the other thing that we were talking about before we recorded this episode was like, hey, we're talking about something I was working on at work, which is completely unrelated to ML engineering, but it's about writing scripts. I was talking about, I had to figure out how to do this grep command that then piped into this sed command. I've never had to know how to do that particular application and use case of that particular grep command, that special command, and then passing it to sed. So I went and learned it and applied it, and now have this understanding, this example of how to do this one esoteric advanced thing. And practitioners in ML who are building models, that's generally what they do when they get into a real world problem. They have to learn it. They have to go really deep on that particular algorithm that they're going to be using. You don't have to do it in order to test a bunch of stuff out. You can test whatever you want. The APIs are high level. They're easy. You can read through the API docs and get a general idea of like, oh, so that's how SVM does this, kind of, I hope. But once you go past that phase of rapid prototyping and you select something that you've tested and seen how it performs on this data set, and you've done a bunch of holdout validation tests, and you've played around with the hyperparameters to understand the response characteristics. Like, hey, is this thing super flaky? Like, if I change this one hyperparameter by 1%, does everything fall apart? Well, maybe that algorithm's not so good for your data. It's probably good for some other use cases, but not this particular one. And that's what an experienced ML person will do is test that out, find out which one really works well, and then go deep in that. I can't even tell you how many times I've broken open books on projects that I've worked on where I'm like, I've never used this particular form of generalized linear models before. I've never used this particular implementation of this equation. I'm going to open up books from college, which I still have all of them, and I'll read through that chapter and I'll read through it again and then 3 more times throughout that project so that it really cements in my head, like, hey, when I'm messing with this parameter, this is what it's doing to this equation. And that's why I see this behavior in the results. And if I need to do simulations of like, well, what if we get real world data that's so far different than what we currently have in validation and in training, what does the model actually do? And generate those synthetic feature vectors and pass them through and make sure, hey, is this going to start predicting something that is completely impossible? If so, that's fine. I just need to have a conditional on the output of the predict where it says, hey, if the prediction is above this value, then cap it at this. Or if it's below this value, I don't want to expose a REST endpoint API to an end user where I'm pushing out positive or negative infinity or not a number because it can't actually calculate something beyond 64-bit integer space. Whatever it happens to be, like some funky thing, I'll go and test that because I've gone and learned how that algorithm works. I know that if I'm using tree-based algorithms, I don't have to do that. I'm constrained by the very nature of how that algorithm works. I can't predict something that I haven't seen before. So I don't need to worry about extreme outlier predictions. A linear model? Oh, I definitely do have to worry about that because there is no constraint. It's an equation. And depending on what the shape and nature of that is and how I've scaled that data as an input into training and making sure that I'm applying that exact same scaling factor to my predictions, then I can be pretty safe knowing that I'm putting in proper controls on that production side so that people aren't saying, wow, data science team, a bunch of idiots. Look at this. Like, look at the junk predictions that are coming out of this model. That's kind of how I approach it.
Hi, this is Charles Max Wood from Top End Devs. And lately I've been coaching some people on starting some podcasts and in some cases just taking their career to the next level. Whether you're beginner going to intermediate going to advanced, whether you're trying to get noticed in the community or go freelance, I've been helping these folks figure out how to get in front of people, how to build relationships, and how to build their careers and max out and just go to the next level. So if you're interested in talking to me and having me help you go to the next level, go to topenddevs.com/coaching. I will give you a 1-hour free session where we can figure out what you're trying to do, where you're trying to go, and figure out what the next steps are. And then from there, we can figure out how to get you to the place you want to go. So once again, that's topenddevs.com/coaching.
What if you're coming from a place, and I know we're diverging a bit from hyperparameter tuning, but what if you're coming from a place of maybe you aren't super familiar with a lot of methods and learning this stuff will take time and you have a week to deliver this project? You could go in, read textbook chapters, learn what every hyperparameter does, do that while you're doing EDA, feed engineering, taking care of your kids, whatever else your life involves. Do you have a rule of thumb to know that like this will probably be a good enough understanding to implement this and troubleshoot and have reliable results? Do you have any framework around thinking that, or are you more just make sure you know everything pretty well so that you can handle everything?
I have a flippant answer to that. If you're working for a company that gives you a week to implement an ML solution, it's time to find another job because that company sucks and the management is clueless. But a serious answer to that, most ML projects, if you're using machine learning in something, you should be communicating to management and communicating to project managers about what that process actually is. And you devote time for these sorts of things. If you're a company that's been working in image detection for years and you have some old school computer vision stuff that's not deep learning. And you, over the last couple of years, you've been doing a bunch of deep learning stuff. And you have all these CNNs and all these adversarial networks that are working to generate images and labels for them and whatever else that you're doing. If all of a sudden a project comes up where you're like, hey, we need to do text analysis. So we need to do NLP for this project. If nobody has been working in that space and you have no experts on that team and it's new to that company, you don't take what the project delivery time is for yet another CNN that you're you're already experts on and have a deep understanding of, and say, yeah, it should take like 2 months. No, it's not going to. You need to factor in to say, we're going to do experimentation and prototyping that's going to be 4 times longer than we would for any other project, because we need to get up to speed on all this stuff. We need to test a bunch of things. We need to read the docs and really understand how these APIs work, and get budget to buy a copy of a couple of NLP books for everybody on the team. Have everybody read about, oh, this is how this stuff is done, and have a little mini hackathon where you're taking some open source data set and the team lead gives a question like, hey, let's see if we can get sentiment analysis on Twitter. And since we need to do it real time for our application, let's do it on the Twitter feed itself. Let's spin up Kafka, let's ingest tweets, and let's see how our models do. And everybody, we have an entire sprint, whether it's 2 weeks or 3 weeks, depending on the ML team. Like that sprint, everybody's just working on that hackathon, except whoever's on call. Whoever's on call does it the next sprint. And then at the conclusion of everybody's work being done, you share it all in the team. You look at everybody's code. You share what you all have learned about, like, hey, did anybody else struggle on this part? This was a tricky part. And then somebody's in the team's going to be like, oh yeah, I solved it this way. And in the process of doing that, you're documenting that for internal references for that team about, hey, here's the things we need to think about when we're building this project. Then you scope and build. But throughout that entire scoping process and MVP construction process, you're going to be learning that API and that process, and you're going to be screwing tons of things up if it's a new thing. So it's always an iterative process. So I don't ever have like, oh, this is good enough. I always think it's never good enough. Even the people that build those algorithms, now speaking as someone who is in a group that does that, when we're going through that level of understanding of how something works or how to actually build it so that other people can use it, we don't have all the answers. Nobody does. But we also don't say, it's good enough. If a bug comes up or we have a test failure, it's not like, we'll fix that later. It's no big deal. It's like, no, we fix it now. But in the process of fixing it now, you go and research and figure out exact root cause. And in the process of figuring out root cause of why something went wrong, you're going to learn so much about how something is built or what the theory is behind it. And that just helps you out in the future. So always learning, always growing is the TLDR of that.
Yeah. I agree. I think that it's often you're time pressed in whatever you're working on, and you try to, like, sometimes people take shortcuts and sometimes they backfire and sometimes they don't. But if you really want to be writing code that is maintainable and effective, and that you won't have to work on again, hopefully, it's important to really know what's going on behind the scenes. Because I've been bitten way too many times just trying to go fast and trying to churn out projects without actually knowing what's going on. So sometimes slowing down and really getting like creative and asking questions, like Ben was saying, like, oh, I wonder what happens if I change this parameter to this, or I wonder what happens if I remove this variable. That can have dramatic impacts on the product. And it might be dramatic as in a difference in a value of a hyperparameter, but that is dramatic in terms of output, because these models are so sensitive that if data changes and this hyperparameter is a bad value, then it can completely throw off results relative to a better parameter value. So cool. Back to parameters. What about like linear regression and GLMs? What are some defaults and what are the things you usually play with?
I mean, there's fewer things that are available in those models. And if we're talking about sklearn, when we go from the tree-based stuff into linear models, there's a lot of flavors that are in existence. And it's about how does the optimizer and what is the logic that the optimizer is using in order to determine what to test, how to evaluate it, how far to go from priors when looking at those feature vectors. And the features are your coefficients in that equation. And it's going to make adjustments to the coefficients that are applied to the feature values in that iteration. Some linear models have hyperparameters that are related to, like the magical one in sklearn, your L1 ratio. In other ones, it's the alpha value. Other ones is like fit intercept. So all of these are changing the way that features are either filtered out or capped or removed from evaluation based on like, hey, this is so far outside of, like, in order for me to optimize around this particular outlier value, I need to exclude it from estimation, like lassoing. So a good thing to try whenever looking at linear models is the first thing is, what is the distribution of your target? And that alone is going to limit the explosively large realm of possibilities for you. And that's generally what I'm talking about, like generalized linear models, where you're going through and looking at the distribution, like, hey, is this a normal distribution? If so, then you don't need GLM for that. I mean, you use a flavor of GLM called linear regression, and you could be looking at ElasticNet, which is, shares comparisons of the L1 and L2 regularization parameters. So it's a hybrid sort of linear model. It's a little bit ridge, it's a little bit lasso, mixed together. If you're looking at something that is gamma distributed or Poisson distributed, you have a distribution on display there for that regressor that is definitely not normal, is not uniform, is more uniform like. You should be using the right solver or the right model type for that problem. Otherwise, you're going to have to do a lot of extra work, potentially, like transforming your target to force it to be normal. You don't necessarily have to do that with the GLM. You can just tell it, like, hey, this is Poisson distributed data. It's optimized to solve for that problem based on how that algorithm is written and what that formula is for calculating it, and use that. So I always do that first. With linear models, you should always be looking at transforming your features. And what that means is when you're looking at the numeric values within that feature, things should be scaled, and they should be scaled in a way that is mathematically efficient. That does not mean, oh, well, everything's a float, so it's good. When you're looking at that, what is the magnitude and difference between feature 1 and feature 2 and feature 3? Does feature 1, is it in the range of 0 to 10? And then feature 2 is in the range of 10,000 to 10 million? If so, that linear model is going to struggle with its arithmetic in order to figure out what those coefficients need to be and what the dominant effect is on that fit. And a great way that I have communicated that to people who have worked on teams that I've been on, and they're building a linear model and they don't scale that data, I just ask them to plot. I'm just like, hey, plot this feature against this other feature. And they're like, well, okay, well, here you go. And they create something in Matplotlib or Seaborn or something. And then I tell them, like, okay, well, that plotting tool automatically did something for you to make that plot be legible. What do you think it is? They're like, well, it scaled the axes. I'm like, okay, set the axes to the min and max of the bigger one. I want to see everything from feature 2 and feature 1 all on one plot. No cutting off stuff and have it display outside of the plot area. And they do that, and it looks like a vertical line or a horizontal line. I'm like, well, that's what your model is saying effectively, is how do you optimize to something like that? Mathematically, can it be done? Sure. But what is the effect going to be when that feature 2 that is a million times bigger magnitude than feature 1, like, how is that equation going to behave with the variance within that feature 2 compared to variances that happen in feature 1? Your coefficients might reflect that in the final model that's produced, but it's not going to be as effective as if you scaled everything between 0 and 1. So that's really important stuff. But a lot of the hyperparameters, you're going to be tuning stuff that is not intuitive based on the data. From what my experience is, that's more of a condition where I'm approaching that from, okay, I know what the L1 ratio does and about how it's effectively filtering out, individual features while it's going through and making sure that it's not overfitting to obnoxious outlier data. So I'll set a range on that. I won't do, manual tuning to see where, generally this thing should be. I'll use an automated hyperparameter tuning algorithm, or if I'm feeling lazy and I don't want to pip install that package, I'll just do a random search. Like, hey, from 0 to 1, these are the ranges, search 50 iterations, and just to see, like, where is it performing better. And I'll take the results of each of those iterations and what the parameter was versus what the holdout score was, not the cross-validation score, but the holdout score. And I'll plot that and I'll see, oh, well, it looks like it's best between 0.01 and 0.2. So I'm going to write that down somewhere so that when I'm actually using HyperOpt or Optuna or something, that's going to be my search space, because I did a brute force approach at first and found, like, wow, I definitely have this this optimization range. And I'm using my eyes and my plot to do stochastic gradient descent, looking at, okay, here's where the global minima seems to be. And that's kind of the range where I want to search.
Hey, folks, if you love this podcast and would like to support the show, or if you wish you could listen without the sponsorship messages, then you're in luck. We're setting up new premium podcast feeds where you can get all of the episodes released after Christmas 2020 without the ads. Signing up will help us pay for editing and production, and you can go sign up at devchat.tv/premium.
Yeah. So it sounds like there aren't really hyperparameters that you play with other than the elastic net params. And I was just looking at linear model linear regression for sklearn, and there are a total of 5 parameters. One is fit intercept, the second is normalize, and then the rest are just about how it's run, like number of jobs to use for the computation and things like that. So with these much more similar, or simple, excuse me, not similar, with these much more simple models and using more old school techniques, you have to think a lot more about the data, get more creative with the data. But with decision trees, they handle complex data types really, really well. So that scale that Ben was talking about with the 10 million versus 100, let's say, a decision tree will pick that up and you don't actually have to normalize. It sounds helpful for interpretability, but it's not necessary. So going back to another point that we were talking about, if you don't know how these models work, you won't know that a coefficient on a variable that has a scale from 10 million to 100,000 will look very different from a variable that has a scale of 100 to 1. Those coefficients will be very incomparable. But if you normalize or standardize or just rescale your variable, suddenly you can interpret what's going on. Mm-hmm. So I agree that on the for linear-based models, a lot of the optimization for hyperparameter tuning is actually in the feature engineering portion. So that was interesting to see. In the little bit of time that we have left, throughout this whole podcast, we've basically been talking about manual tuning. Ben, you suggested maybe loop and try a bunch of different variables for your lasso versus ridge parameter. But what are some other automated methods that you like to use that maybe aren't hyperopt or optuna? Because that's a whole other topic.
I'll tell you what I don't use, and I probably haven't used it in at least 7 years, is grid search. That's probably another highly unpopular opinion, but hear me out real quick about why I don't use that. It's about time. While working through a project as a data scientist or as an ML engineer, and you're having to create a production version of something that's solving a business problem, you really only have so much time. I talked earlier about, hey, when you're starting a new project that you've never worked on before, you should buffer in some time for doing spikes and understanding what you're about to get yourself into and validating, can we even solve this? Yes or no? But when you've already committed, like that's already done. You've already said, when you're talking about tuning a model, you've already said, yeah, we can solve this. We have a pretty good prototype that seems to perform somewhat okay. When you're tuning, you're in the realm of it's go time. It's usually the last set of things that you're doing because the pipeline's already built. You already have your infrastructure. You know when the training is going to run at particular times. You know, if you're using a passive or active retraining system, you know what all the ML ops infrastructure is looking like. You have CI in place. You know, everything's all pretty much done. And your last thing is, let's see how good we can get this. And that's an iterative process as well. This is something that happens over time. So on a time-based perspective, grid search is terrible. In order to search an effective range of parameters for particular models. Now, this isn't exactly applicable to linear models because you just don't have that many hyperparameters that you could be tuning unless you're looking at esoteric things. You know, some of the generalized linear models, they have a few more hyperparameters. But even still, if you're doing grid search, you're defining values, like discrete values to test. And what is the default human behavior for selecting things to test across a space? We are creatures of patterns. We love pattern matching. Like our brains are wired to do it. And because our brains work that way, if we were given a range between 0 and 1, what are we always going to select? We're either going to generate a range by 0.1 to say, hey, here's my 10 things I'm going to test. I'm going to test 0, 0.0, 0.1, 0.2, 0.3, 0.4. And you're going to do all of those tests. And then that's sort of one problem is you're selecting something that is assuming a linear relationship between its scale and the response. And in most of these hyperparameters, with the exception of some of the stuff with decision trees and random forests. But stuff with linear models, that hyperparameter is not on a linear scale. So it's usually on a logarithmic or an exponential scale. And knowing that off the top of your head, you may memorize that. You may be like, oh, I know I have to check 1e to the negative 9, 1e to the negative 6, 1e to the negative 2, 0.1, 1, 10, 100, and 1,000. You may just instinctively remember that. But the vast majority of the time that I see people use grid search CV, they don't know that. I can't even tell you how many times I've seen a linear search through a nonlinear space. And they end up getting a value that they're like, 0.1 is always the best. Like, yeah, based on what you searched, because everything above 0.2 is garbage and is effectively equivalent, because that's the wrong area of the search space. Let's try a much, much, much smaller number and see what that is compared to 0.1. And then they see that. They're like, whoa, I had no idea. It's like, yeah, that's why grid search sucks, because it relies on us to make those decisions that we might, in a time crunch, not be aware that we're making a mistake of not even searching the optimal space. The other thing is grid search for certain algorithms that have a lot of parameters that you need to tune or need to explore. It's a permutation generator. So each of those elements that you're adding in there, take the count of that times the number of things in your next parameter, times the number of things in your next parameter search space, and so on. If you've got 10 parameters to search through and you're going to do 5 iterations each, good luck explaining that to whoever is hoping to see a result by the end of the day, or whoever is paying the bill on where you're running that search. You're not usually going to learn that much from all of those permutations. A lot of those searches that you're going to be doing are not going to perform any better than anything else. That response of that one parameter in a mix of a whole bunch of other ones might be completely irrelevant. So you're repeating a test many times over. If something is not really moving the needle, you're not learning anything. So I'm always a big fan of random search. So I'll set bounds. And if I need to transform something from a nonlinear space to a linear space so that I can use a range, I'll do that. And tools like what we mentioned, Hyperopt and Optuna, they give you the ability to do that, so you don't even have to think about it. But if you're doing it manually, should be setting something to say, hey, this is a nonlinear search that I want to do. But then you just say, hey, search in the space for each of these parameters, and here's the number of runs I want to do. And there's some great white papers that have been written about this exact contentious debate between explicit searching through grid search versus random search. And the results of all of those papers that I've read show that random search always wins out on both time and, shockingly, usually accuracy. It finds better parameters than manual grid search, unless you're doing like 10,000x the number of searches through grid search than you are through random search. But random search is really good. It's not as good as some of the other stuff.
How does it find better parameters?
It's not locked into the positions that a human decided.
Got it.
Since we like order, the probability that we're going to miss the optimal setting, because we're sort of stratifying this search space by these discrete parameters, we're missing this huge testing space with grid search. Whereas random search, it's just generating a random value between these two numbers, or it's randomly picking a value from a nominal list of values that it could use. And given enough iterations, you're not going to get a good result generally, unless you just get really lucky. If you're like, random search, just do 4 iterations, it's not really searching the search space. But if you do random search 100 and then do the exact same test of grid search for 100 iterations, random is guaranteed to search more of that search space than grid search would be able to, like guaranteed.
Yeah, I think you hit the nail head. The fact that hyperparameters are not uniformly distributed, you shouldn't search them uniform. So random search, it sort of searches it uniformly, but it doesn't have those grid intervals that you mentioned. So it can find stuff in between the spaces of grid search, essentially.
Yep. And some packages allow you to short circuit that random selection, or you can generate your own. If you need to search between 0 and 1 and it's an exponential scale, you can use NumPy random number generator between those values and then transpose it into that scale. So you need to convert it from logarithmic or into a logarithmic value from a linear scale. Just write that equation. It's super simple, but just do it from the generated random number.
Yeah, that makes a ton of sense. I don't ever use grid search. I either manual tune because I'm trying to learn about the data, And that's rarely for a production prediction model. Let's say it's more about EDA exploration and that nature. Or I go the full other route and use something that intelligently searches the search space. So HyperOpt is a classic. But again, not enough time for that.
No, that's a 2-episode discussion topic. Like, what is HyperOpt? What is tree of bars and estimators? How does that thing work? What is Bayesian optimization? What are genetic algorithms? Yeah, someday in the future, we'll talk about that. And we can even talk about a hybrid approach that I built many years ago that was designed for doing this, that hybridizes genetic algorithms and Bayesian search. It's pretty fun stuff. It's just not the most complex to understand when looking at the code. Yeah, production use cases, you're going to be using something automated because it's just going to do a better job than anything else that's out there. And really, when you're retraining something in prod, you're like, hey, it's been 6 weeks since the model was last trained. It's kind of fallen apart. Or, hey, we have this drift that occurred. The features shifted because whatever we're modeling has changed in reality. If you're going back and doing grid search on top of that, that's just an exercise in frustration. You're like, hey, I'll kick off the grid search job and see what the parameters need to be. Well, if you didn't change anything else about that model, you just need to retrain it and make sure that it's accommodating this new distribution shift in data. Chances are your hyperparameters need to change a little bit to adapt to that. If you just do a blind retraining with prior values, there's no guarantee that it's going to perform the same, and it could just fall apart. So pretty important to have automation in place for that.
Yep. Could not agree more.
All right. So this was a fun one that opened up the Pandora's box and some other future episodes that we'll be doing. But next week, I think we have an actual guest on where we'll talk about some stuff that they've written, have some fun with that. So until next time, everyone, thanks for tuning in. I've been Ben Wilson.
And Michael Burke.
And we'll catch you later.
Bye, everyone.
Bandwidth for this segment is provided by CacheFly, the world's fastest CDN. Deliver your content fast with CacheFly. Visit CACHEFLY.com to learn more.